All right, I wanted to do a little bit more work with series and parallel circuits, mainly to provide some practice with the rules we've learned and maybe practice a few more examples. So here we have a parallel circuit, and one of the rules that I went over in the previous video is that all branches in a parallel circuit are independent of each other. Now, this rule comes into play when one starts adding and removing branches, and many test questions will ask what happens to the current through branch 1 when you remove the resistor in branch number 3. And the answer is that nothing is going to happen to the current down branch 1 or branch 2 if you remove the resistor from branch 3. However, if these resistors were in series, then there would be a big dependence, because when you put resistors in series, if you remove one of them, then you've broken the circuit and the entire circuit would shut down. So although they don't affect each other in parallel, they very much affect each other when they're in series. So in the previous video, I reviewed how potential difference gets dropped or lost at the various resistors. Here we have an R and a 2R, and we have a 120 volt cell or source of potential difference. And the question would be, how much of the 120 gets dropped at the resistor R and how much at the 2R? You should probably pause the video and think about your answer. Well, in the previous video, I discussed the fact that in a series circuit, the potential difference gets dropped in proportion to the size of the resistors. So just like in an obstacle course, you would want to save more of your energy for the 2R resistor and less for the R. Since they're in a 2-to-1 ratio, that means the potential difference will get dropped in a 2-to-1. So that means that we would lose 80 volts at the larger resistor and 40 volts at the smaller resistor, so that the drops are in the 2-to-1 ratio, and the larger resistor gets the larger potential difference. In the last video, we also discussed how current branches when you have different size resistors in the branches. If 12 amps of total current flows, you should be able to predict how much of that current will flow down the R branch and how much down the 2R branch. You should pause the video and think about your answer. All right, in the previous video, we discussed the rule that in a parallel circuit, the current will branch in proportion to the size of the resistors, but this time, more of the current goes through the smaller resistor. So it's the same ratio, but now instead of the larger resistor getting more, it's going to get less because current takes the path of least resistance. So if we have 12 amps of current and the resistors are in a 2-to-1 ratio, that means we're going to have 4 amps and 8 amps. However, the 8 amps will go down the smaller branch, 8 amps, and 4 amps will go down the larger resistance branch. We should also be able to think about what's going to happen when you change a circuit. For example, what would happen if we added another resistor to the following circuit? We would want to know what would happen to REQ and what would happen to I total. You might want to pause the video while you think about what would happen to these two quantities if you added a third resistor. All right. Let's first talk it out and then we'll calculate it. If we add another resistor due to the equation for equivalent resistance where you add the resistors together, you would think that resistance would go up. So we'll make that prediction. And the effect on the total current, well, if resistance goes up, Ohm's law tells us that current and resistance are inversely proportional to each other. So if total resistance goes up, that would mean that total current should go down. Let's take a look. I selected easy numbers so we could do the math in our head. So the total potential difference here is 60 volts and the total resistance is 20, and V total divided by R total, 60 divided by 20 will be 3 amps of current. That's the original current flowing in the circuit. So now, what happens if we add another 10 ohm resistor? Well, to be certain, the 3 amps will not flow anymore. If the equivalent resistance becomes 30 ohms, I total will be V total over R total, and 60 volts over 30 ohms will now be 2 amps of current. So as predicted, when we added a resistor in series, the equivalent resistance went up and the total current went down. If you look at your rules for series circuits, it says that I total equals I1 equals I2 equals I3. That rule often leads people to believe that the total current can never change in a series circuit, and here the current went from 3 amps to 2 amps when I added an additional resistor. So how do we reconcile that behavior with our rule? Well, the rule I total equals I1 equals I2 equals I3 doesn't say that you can't change the current in a series circuit. What it does say is no matter where you put an ammeter, it's always going to read the same value everywhere in the circuit, which would be 2 amps everywhere as drawn. But if we go back to the original circuit, all of these meters would read 3 amps. So yes, you can change the current flowing in a circuit, but every time you change it, the current everywhere in the circuit must be equivalent. Let's do the same thing for parallel circuits. Here we have a 120 volt source of potential difference and two 60 ohm resistors. You should probably pause the video and think about the effect of adding one more resistor on the equivalent resistance and the total current. So first we'll make our prediction. If we add another resistor, as previously discussed, even though it doesn't make sense, the equivalent resistance will go down if you add another resistor. And since current and resistance are inversely proportional, that should mean that the total current should go up. Let's check the prediction with some math. Here we have two 60s in parallel. If we use our rule of thumb about identical resistors in parallel, we would take the resistance of one of them, 60 ohms, and divide by the number of resistors, which would be 2. So 60 over 2 would be 30. So the equivalent resistance originally will be 30 ohms. Now, how much current will flow when you connect an REQ of 30 ohms to a potential difference of 120 volts? Well, Ohm's law tells us that that will be 4 amps of current. Now, what happens if we add another resistor? Let's add another 60 ohm resistor in parallel. So what does that make the new equivalent resistance? Well, once again, we can use our rule of thumb. We have identical 60 ohm resistors and 3 of them in parallel. So take the 60, divide by the 3, and we now have a new equivalent resistance of 20 ohms. So as predicted, the equivalent resistance went down. What does that do to the total current? Well, since they're inverses of each other, the total current goes up. So the math indeed backs up our original predictions. Now let's try an example. This wonderful example comes out of Physics Teacher magazine. Yes, there's such a thing. Here we have 3 identical light bulbs, but now they're connected in a series parallel combination. Whenever one solves a series parallel combination, you could ask yourself, does this circuit look mainly series with a touch of parallel, or mainly parallel with a touch of series? In this particular example, the circuit is clearly mainly parallel with 2 main branches, but in one of the branches you have bulbs A and B in series. So I would call this one mainly parallel with a touch of series. So the backbone of the circuit is parallel, and let's think about it in that fashion. They tell us that the source of potential difference is 12 volts. So let's write 12 volts on our battery. And each of the bulbs is 12 ohms. I'll just write that once. So each bulb is an equivalent 12 ohms. So it says, what is the current in each lamp? Let's take the first branch first, the one with bulb C in it. If we have a 12 ohm resistor or lamp and it's connected to a 12 volt battery, the current through bulb C, IC, will be VC over RC. And we only know V total, but if you look at your rules, since V total equals V1 equals V2 equals V3, that means that this V total is the same as VC. So the total current flowing in this branch through bulb C is going to be 12 volts on top divided by 12 ohms on the bottom. So we're going to get 1 amp of current flowing in bulb C. Now what about the current through the top bulbs? Well, through the top bulbs, the same current is going to visit each bulb. So what we probably ought to do, since they're in series, is to combine them. So the top has an equivalent resistance of 24 ohms across the top because we have A and B, each of which is 12 ohms in series. So we're essentially putting a 24 ohm bulb connected to a 12 volt battery. If you use Ohm's law, since the V up here is 12 and the resistance is 24 ohms, that means the current through A will be the same as the current through B, and they'll both be a half of an amp, 0.5 amps. Struggling with the mouse here. It'd be much better if I had my smartboard. Now, so what is the total current? They didn't ask this, but let's ask the question, what's the total current leaving the battery? What is I total? Well, you might be tempted to say that it's 2 total amps because bulb C gets a 1 amp and bulbs A and B get a half an amp each. The reason that's not correct is it is the same half amp that flows through A and B. So the correct answer to what the total current leaving the battery would be, or is 1.5 amps. The bottom branch gets 1 amp, the top branch gets a half an amp, which visits both A and B, but again, it's the same half of an amp. Now on to question 2. What is the voltage or potential difference across each lamp? I think that's a little easier. The potential difference across A, since A is connected directly to the battery because of its parallel nature, we'll see the full potential difference of 12 volts. Now, A and B are connected to the battery, but they're connected in series. That particular outside branch has 2 resistors in it, and remember Kirchhoff's second law, it says whatever potential you gain at the battery, 12 volts, you must lose out in the circuit. So here, if we gain 12, that means we must lose 12 up here, so it must be 6 apiece. So the potential drop across A will equal the potential drop across B, which is going to be 6 volts each. So 12 volts, 6 volts, 6 volts. Let's skip the power dissipated each lamp, but let's talk about what happens to the power dissipated in the bottom branch if you unscrew bulb A. Why don't you pause the video and think about that? Well, we've already discussed the rule that all branches in a parallel circuit are independent of each other. So if you unscrew bulb A, that will actually break the top branch and bulb B would go out. But the question is, what happens to the power dissipated in lamp C? The answer is absolutely nothing, because all branches in a parallel circuit are independent of each other. What happens to the power dissipated in A if lamp C is unscrewed? Well, A and B are in the top branch, C is in the bottom branch. If you unscrew bulb C, that will have absolutely no effect. So this answer can come down here as well, no effect. All branches in a parallel circuit are independent of each other. Our final example, we have a hefty series parallel combination. And the question is, will a 2 amp fuse blow if it's placed near the 10-volt battery? So here you can see our 2 amp fuse near the battery, and we have a bunch of resistors out here. Now, what's it really asking if a 2 amp fuse will blow when it's placed near the battery? Which current should we calculate? Well, the answer would be, we need to find the total current flowing in the circuit. If we can find I total, that's what flows through the fuse. Incidentally, it's also what flows to this 8 ohm resistor here. This is an 8 ohm, a 3 ohm, a 30 ohm, a 10 ohm, a 5 ohm, a 4 ohm, and a 12 ohm. I know it's hard to see those decimal places. If we can find the total current, then we will know if the fuse will break or not, whether it's greater than or less than the 2 amps. So how do we know? Well, I total, thanks to Ohm's law, I total is V total over the equivalent resistance. And we know the V total is 10 volts. And the equivalent resistance, if we can find that, then we have the answer to our question. So how do we find the equivalent resistance of this mess? Well, you need to notice that we have some areas that are parallel in this circuit. That area there and that area right there. We have a 4 ohm and a 12 ohm. And here we have a 30, a 10, and a 5 ohm. Why don't you pause the video and find the resistance of those two areas? If you did your 1 over rule correctly, you'll see that you have a 3 ohm resistance here and also a 3 ohm resistance up there. Now this entire circuit is starting to change. We have an 8 ohm resistor still up at the top. We have a 3 ohm resistor still here, but now in this outside branch, all three of these top resistors can be replaced with just a 3 ohm. And over here, the 4 and the 12 can be replaced with just a 3 ohm. Now the circuit's starting to look a little more simple. Can we combine anything else? Well, sometimes I hear that all three of these resistors are in series, but they're not. Things are only in series if there's no junctions between them, and we have a junction right there. So the only thing we can say is in series are these two resistors right here. We have a 3 and a 3, which adds to a 6 in series. So we still have this 8. We still have this 3. That's an 8. That's a 3. And this outside branch, because they're in series, the 3 and the 3 just added to a 6. Why don't you pause the video and see if you can figure out what the equivalent resistance is of this remaining arrangement of 3 resistors. Well, hopefully you noticed that these two resistors are in parallel with each other, and a 3 and a 6 in parallel, if you do the 1 over rule on your calculator, will get you to 2 ohms. So essentially this circuit is an 8 ohm resistor and a 2 ohm resistor in series for a grand total of 10 ohms. So all of this resistance up in the top, when you break it down, will get you to 10 ohms. So we have 10 volts and we have 10 ohms for V total and R total, which will give us 1 amp of current flowing through the battery. Incidentally, not only will 1 amp not break that fuse, if you were looking for the current through this 8 ohm resistor, you would also answer 1 amp because obviously the total current flows through that resistor because there's no branches between there and the battery. I hope all these rule reviews and examples help your understanding of series and parallel circuits.